There is a place in the universe where the laws of physics stop working, not where they become difficult to apply, not where they produce results that are hard to measure or complicated to calculate, where they stop, where the most successful and precisely tested theory of gravity ever constructed. A theory that has predicted the behavior of everything from the orbit of Mercury to the detection of gravitational waves from collisions a billion light years away, reaches the edge of what it can describe and produces, in place of an answer, a mathematical breakdown so complete that the equations themselves tell you they have nothing left to say. That place is a black hole, and almost everything you think you know about it is either incomplete or wrong. Not because the popular accounts of black holes are careless, most of them are not, but because black holes are genuinely, irreducibly strange in ways that resist the kind of clean summary that fits in a headline or a school lesson. The closer you get to what a black hole actually is, the more carefully you follow the physics rather than the metaphors, the more the familiar picture dissolves and something far more disturbing takes its place. Something that raises questions about the nature of space, of time, of information, and of reality itself that physics has not yet answered, and may not answer for a very long time. If this is the kind of content you want more of, subscribing to The Cosmic Depth takes 2 seconds, and we post new documentaries every few days, because we are going to start from the beginning, not from Hollywood, not from the cultural image of a black hole as a cosmic drain, a tunnel through space, a monster waiting to devour passing spacecraft, from the physics, from the actual mathematics and the actual observations and the actual implications of what those mathematics and observations are telling us about the structure of reality. And it is considerably stranger than the monster. Start with gravity. You think you understand gravity. Everyone thinks they understand gravity. It pulls things down. It keeps planets in orbit around stars and moons in orbit around planets. It is the force that shapes the large-scale structure of the universe. The force that coalesces gas clouds into stars, that organizes stars into galaxies, that draws galaxies into clusters and clusters into the vast cosmic web that stretches across the observable universe. You have felt gravity every moment of your life. You have never been outside its influence. It is the most familiar force in the universe, and almost nobody understands what it actually is. Newton described gravity as a force, an invisible pull acting at a distance between massive objects, proportional to their masses and inversely proportional to the square of the distance between them. Newton's description was extraordinarily successful. It explained the motion of the planets, the behavior of tides, the trajectory of cannonballs. It was the foundation of celestial mechanics for 2 centuries. Newton himself was deeply uncomfortable with it. He knew that his description of gravity was not an explanation. Calling it a force that acts at a distance without any physical mechanism to transmit that force across empty space was, as he privately acknowledged, an absurdity. He described the phenomena. He refused to hypothesize about the mechanism. His famous phrase, hypotheses non fingo, I frame no hypotheses, was not a statement of satisfaction with his theory. It was an admission that something fundamental was missing from his understanding. What was missing waited 2.5 centuries for Einstein to provide it. In 1915, Einstein published his general theory of relativity. And general relativity did not simply improve on Newton's description of gravity. It replaced the entire conceptual framework. It said that gravity is not a force at all, it is geometry. Mass and energy, in Einstein's theory, do not pull other objects toward them through some mysterious action at a distance. They curve the fabric of spacetime, the four-dimensional structure in which all events in the universe occur. And objects moving through that curved spacetime follow the straightest possible paths through it. What we experience as the pull of gravity is not a force acting on us. It is us following the geometry of the spacetime that mass has curved around us. The Earth does not pull the moon toward it. The Earth curves the spacetime around it, and the moon moves through that curved spacetime on the straightest path available to it, which happens to be an orbit. This is not a metaphor. It is a precise mathematical description that has been tested to extraordinary accuracy in dozens of experiments and observations over more than a century. The bending of light around massive objects, predicted by general relativity, and confirmed by Eddington's famous 1919 eclipse observation. The precession of Mercury's orbit, which Newton's gravity could not explain and general relativity predicts exactly. The existence and properties of gravitational waves, ripples in the fabric of spacetime itself, generated by accelerating masses, detected directly for the first time in 2015 by the LIGO Observatory and now routinely observed from merging neutron stars and black holes across the universe. General relativity is not a tentative theory. It is one of the most precisely verified theories in the history of science. And one of the things it tells us, with mathematical certainty from the equations themselves, is that black holes must exist, not as exotic exceptions, not as the products of unusual cosmic circumstances, as inevitable consequences of what gravity does when enough mass is concentrated in a small enough space. To understand why, you need the concept of escape velocity. Every massive object has an escape velocity, the minimum speed, at which another object must be launched in order to escape the gravitational pull of the first object and travel away from it indefinitely rather than being pulled back. For the Earth, escape velocity is approximately 11.2 kilometers per second. Launch something faster than that, and it escapes. Launch something slower, and gravity pulls it back. For the Sun, escape velocity is much higher, about 617 kilometers per second. For a neutron star, the collapsed remnant of a massive star after a supernova explosion, an object with more mass than the Sun compressed into a sphere roughly 20 kilometers across. Escape velocity is a significant fraction of the speed of light. Now ask what happens as you make the object smaller and denser while keeping its mass the same. Escape velocity increases. Keep compressing. Keep increasing the density. At some point, at a specific radius called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who calculated it. From Einstein's equations in 1916 while serving on the Russian front in the First World War, the escape velocity reaches the speed of light. And at that point, something qualitatively new happens. Because the speed of light is not merely the fastest thing in the universe. It is the maximum speed at which any information, any influence, any causal connection of any kind can propagate through space. This is not a technological limitation. It is a fundamental feature of the structure of space-time itself, a limit built into the geometry of reality at the deepest level. When the escape velocity of an object reaches the speed of light, light itself cannot escape. Nothing can, not matter, not radiation, not any signal of any kind. The region of space within the Schwarzschild radius becomes causally disconnected from the rest of the universe. What happens inside cannot influence what happens outside. Information cannot get out. Light cannot get out. A black hole. Schwarzschild found. This solution almost immediately after Einstein published his equations. He sent the result to Einstein from the trenches, and Einstein was reportedly astonished that an exact solution existed at all. He was also initially convinced that the physical object described by the mathematics could not actually exist in nature. The concentrations of mass required seemed impossibly extreme. Surely some physical process would intervene before any real object could collapse to such densities. He was wrong. We know this now with the kind of certainty that comes not from theoretical argument, but from direct observation. The first image of a black hole, captured in 2019 by the Event Horizon Telescope, a global network of radio observatories linked together into a single instrument the diameter of the Earth, showed the shadow of the supermassive black hole at the center of the galaxy M87, a ring of superheated gas glowing orange around a dark, circular region. The darkness at the center was the region from which no light escapes, the black hole that Einstein did not believe could exist. Photographed by human beings using instruments we built. It was there all along, and it is not alone. Supermassive black holes, objects containing millions or billions of times the mass of our sun, sit at the center of almost every large galaxy in the observable universe, including ours. At the center of the Milky Way, approximately 26,000 light years from Earth, sits an object called Sagittarius A, a supermassive black hole with a mass approximately 4 million times that of our Sun. The galaxy you live in orbits a black hole. Black holes are not exotic exceptions at the fringes of the observable universe. They are central features of its structure. They shape galaxies. They regulate star formation. They are present at the heart of the cosmic web of matter that defines the large-scale architecture of everything we can see. But here is what none of those facts prepare you for. None of them tell you what a black hole actually is, what happens at its boundary, what lies at its center, what it does to space and time, and the very concept of physical law as you approach and cross the point of no return. Those questions are stranger than anything the images suggest, and they start at the edge. The edge of a black hole has a name, the event horizon. It sounds dramatic. It sounds like the name of something you would see. A wall, a surface, a visible boundary where space ends and darkness begins. The name conjures an image of a definite threshold, a line drawn across the universe, something that announces itself. The reality is almost the opposite. The event horizon is not a surface. It has no physical substance. There is no wall, no membrane, no barrier of any kind that you could touch or feel or detect with any instrument as you crossed it. It is not made of anything. It is a mathematical boundary, a region of space-time defined entirely by its relationship to what lies inside it, a point of no return that is invisible, undetectable in the conventional sense, and in the case of a sufficiently large black hole, completely imperceptible to anyone crossing it. You could cross the event horizon of a sufficiently large black hole without knowing. There would be no flash of light, no physical sensation, no instrument reading that spiked at the moment of crossing. One moment you would be outside, the next you would be inside. And the only thing that would have changed is this: every path available to you through spacetime, every direction you could travel, every possible future trajectory of every particle in your body would now point inward, toward the center, without exception. You would not have hit a wall. You would have entered a region of spacetime where the future is a place. Let that sit for a moment. In ordinary spacetime, in the universe outside a black hole, time is a dimension. It has a direction, yes. The arrow of time points from past to future in the way we have discussed in previous documentaries on this channel. But within that directional flow, there is freedom. You can move through space in any direction. You can accelerate, decelerate, change course. The future contains many possibilities, and your trajectory through it is at least partially under your control. Inside the event horizon, this changes in a way that is mathematically precise and physically total. The singularity, the point at the center of the black hole toward which everything inside the horizon falls, is not in a direction. It is not to the left or the right or above or below. It is in the future. It is a moment in time, not a location in space. And inside the event horizon, every possible path through spacetime leads toward it. Not because of a force pulling you, because the geometry of spacetime inside the horizon is structured in such a way that inward, toward the singularity, is the only direction that time can flow. You cannot avoid the singularity inside a black hole for the same reason you cannot avoid tomorrow. It is simply where time goes. This is one of the most unsettling results of general relativity, and it is worth sitting with until it genuinely lands. We are not talking about an irresistible, gravitational pull that you lack the engine power to overcome. We are talking about a region of spacetime where the dimension of time itself has been rotated, where what was a spatial direction has become a temporal one, and where the future of every possible physical system inside the horizon is a single, unavoidable point. The singularity is not a place you fall into, it is a moment you fall toward. Now hold two perspectives simultaneously. You are inside the black hole, falling freely, not firing any engines, not resisting the geometry, simply moving through space-time along the path that space-time makes available to you. From your perspective, for a sufficiently large black hole, the crossing of the event horizon was imperceptible. You are now inside. Time continues to pass for you in the way it always has. You can think, observe, measure. You have a proper time, a duration measured by a clock you carry with you that continues to tick forward. How much time do you have before you reach the singularity? It depends on the mass of the black hole. For a stellar mass black hole, a black hole containing a few times the mass of our Sun with a Schwarzschild radius of roughly a few kilometers, the time between crossing the event horizon and reaching the singularity is measured in microseconds, less than a blink. No time to observe anything, no time to think, no time to register what has happened before the tidal forces. The difference in gravitational pull between different parts of your body have stretched you into a stream of particles falling toward an infinitely dense point. This process has a name: spaghettification. It is one of the few pieces of technical vocabulary in astrophysics that is both accurate and genuinely descriptive. Near a stellar mass black hole, the tidal forces are strong enough to stretch any macroscopic object, any object larger than a subatomic particle, into an increasingly thin stream, a strand of matter being pulled lengthwise while being compressed from the sides, elongated into something resembling a strand of spaghetti as it falls toward the singularity. For a supermassive black hole containing millions or billions of solar masses, with an event horizon potentially billions of kilometers across, the situation is qualitatively different. The tidal forces at the event horizon of a sufficiently massive black hole are gentle enough that a human body could cross the horizon without being immediately destroyed. The difference in gravitational pull between your head and your feet at the moment of crossing would be negligible. You would feel nothing unusual. You would have, depending on the mass, hours or even days of proper time inside the horizon before reaching the singularity. Hours or days to observe the interior of a black hole. Hours or days to make measurements, to think, to record whatever you found, with the absolute certainty that nothing you recorded could ever be transmitted to anyone outside. No signal of any kind could escape back across the horizon. You would be in possession of knowledge that could never be shared, a cosmological secret. Now take the perspective of the person who stayed outside. They are watching you fall. They have an extraordinarily powerful telescope trained on you as you approach the event horizon. They can see you. They watch you fall towards the boundary. And as you approach it, something strange begins to happen. You slow down, not because your actual velocity is decreasing. You are falling freely, accelerating under the black hole's gravity. But the light that you emit takes longer and longer to reach the outside observer as you fall deeper into the gravitational well. And as the light climbs out of an increasingly strong gravitational field to reach the outside observer, it loses energy. It redshifts. Its frequency decreases. It becomes progressively redder. And from the outside observer's perspective, your clock is running slower. We discussed time dilation in our documentary on the nature of time, how clocks run slower in stronger gravitational fields, how a clock at the Earth's surface runs slightly slower than one at high altitude. At the event horizon of a black hole, this effect reaches its absolute limit. The gravitational field at the event horizon is such that time dilation becomes infinite. From the outside observer's perspective, your clock stops. You never reach the horizon. Literally. The light emitted by you as you approach the event horizon takes increasingly long to reach the outside observer, and the light emitted at the exact moment you cross the horizon takes an infinite amount of time to arrive. The outside observer never sees you cross. You are frozen at the boundary, your image progressively redshifted until it fades beyond detectability, hanging at the horizon for the rest of the universe's history from their perspective. You crossed the horizon a fraction of a second after approaching it from your perspective. You never crossed it from theirs. Both of these statements are true simultaneously. This is not a paradox in the sense of a contradiction. It is not a case where one description must be wrong. Both are valid descriptions of the same physical situation from different reference frames. Special and general relativity demand that both be taken seriously as accurate accounts of reality. There is no preferred reference frame. There is no objective answer to the question of whether you cross the horizon or not that holds for all observers simultaneously. The event horizon is the place where the observer dependence of physics, the fact that what you observe depends on where you are and how you are moving, reaches its most extreme expression. What happens inside is real and takes a finite, proper time from your perspective. From the outside, it never happens at all. This creates a problem, not just a philosophical discomfort, a genuine, unresolved, technically precise problem at the frontier of theoretical physics. A problem that Stephen Hawking spent the last decades of his life working on. A problem that has consumed some of the most brilliant minds in physics for 50 years and remains unsolved today. It begins with something Hawking discovered in 1974 that nobody expected. Black holes are not completely black. In 1974, they glow. Stephen Hawking did something that should not have been possible for any black hole. He combined two theories that are fundamentally incompatible with each other so faintly general relativity, which describes the large-scale structure of space-time and gravity to build in the quantum mechanics, which describes the behavior of matter in the mathematics of the subatomic level, applied to the curved space-time of a black hole to discover something about black holes that nobody had anticipated, radiation, and the implications of that radiation was followed carefully through the mathematics. He discovered that black holes evaporate. Not just to understand why this is so disturbing, you need to understand something about more quantum mechanics that is easy to state and almost they lead to a conflict at the heart of physics itself. Empty space is not empty. This is not a metaphor or a loose approximation. It is a precise statement about the quantum mechanical structure of the vacuum. In quantum field theory, the framework that underlies our understanding of all fundamental particles and forces, what we call empty space is actually a seething, roiling, fluctuating field of quantum activity. Pairs of particles, a particle and its corresponding antiparticle, are constantly being created out of the vacuum and annihilating back into it, existing for durations so brief that they cannot be directly detected without violating the conservation of energy for a measurable length of time. These are called virtual particles. They are not hypothetical. Their existence has measurable consequences. The Casimir effect, the tiny attractive force that appears between two uncharged metal plates placed very close together in a vacuum, is a direct consequence of virtual particle fluctuations in the space between and around the plates. It has been measured in laboratory experiments. Virtual particles are as real as any other phenomenon in quantum mechanics, which is to say, they are real in the specific, precise, operationally verifiable sense that their effects can be predicted and confirmed. Now, bring a black hole into the picture. At the event horizon of a black hole, Hawking showed something unusual happens to the virtual particle pairs that are constantly appearing and annihilating in the vacuum. Occasionally, a pair appears at the event horizon itself. One particle on the outside, one particle on the inside. In normal empty space, these pairs would annihilate almost immediately. But at the event horizon, the geometry of spacetime separates them. The particle that appeared inside the horizon cannot cross back out. The particle that appeared outside the horizon can escape into space. From the perspective of the outside universe, a particle has appeared at the black hole's surface and radiated away into space. From the perspective of energy conservation, the energy for that particle has to come from somewhere. And the only available source is the black hole itself. The black hole loses mass infinitesimally slowly for any black hole of stellar mass or larger. The Hawking temperature of a black hole, the temperature at which it radiates, is inversely proportional to its mass. A black hole containing several times the mass of our Sun has a Hawking temperature of roughly 100 millionth of a Kelvin, far colder than the cosmic microwave background radiation that permeates the universe. Such a black hole absorbs more energy from the background radiation than it emits in Hawking radiation. It grows rather than shrinks. But wait long enough. Wait for the universe to cool, for the expansion of space to dilute the background radiation below the Hawking temperature of the black hole. Then, the black hole begins to lose mass, slowly at first, then faster as it shrinks and its temperature rises, then faster still. In the final moments, the evaporation accelerates catastrophically. The black hole radiating its remaining mass in a burst of energy as it approaches zero size. And then it is gone. This result, Hawking radiation and the eventual evaporation of black holes, is one of the most celebrated theoretical discoveries of the 20th century. It is the first time anyone successfully combined quantum mechanics and general relativity in a physically meaningful calculation. It earned Hawking an extraordinary reputation and should probably have earned him the Nobel Prize. Though the impossibility of experimentally verifying Hawking radiation from any black hole accessible to current instruments meant the prize was never awarded. But the real significance of Hawking radiation is not the radiation itself. It is what the radiation implies about information. And here, the physics arrives at a place so disturbing that it divided the theoretical physics community for decades and still has not been fully resolved. Information is not the everyday word for data or facts or knowledge. In physics, information has a precise technical meaning. It refers to the complete description of a physical system, the specification of the quantum state of every particle and field in that system, the totality of what would be needed to reconstruct the system exactly. Quantum mechanics has a fundamental principle about information. It cannot be destroyed. This is not a contingent fact about the current state of technology. It is a deep structural feature of quantum mechanical evolution. The unitarity of quantum mechanics, the mathematical property that says quantum states evolve in ways that preserve information. The equations of quantum mechanics guarantee that if you know the complete quantum state of a system at one moment, you can, in principle, calculate the complete quantum state at any earlier or later moment. Information is conserved. It cannot simply vanish. Now follow what happens when matter falls into a black hole. The matter carries information. Every particle that crosses the event horizon carries with it the complete specification of its quantum state, its position, its momentum, its spin, every quantum number that describes it. That information crosses the horizon and is, from the perspective of the outside universe, gone, hidden behind the event horizon, inaccessible. But inaccessible is not the same as destroyed. As long as the black hole exists, the information is merely hidden, locked inside the horizon where it cannot be retrieved, but where it still, in principle, exists. Then the black hole evaporates. And here is the problem. The Hawking radiation that carries away the black hole's mass as it evaporates is, according to Hawking's original calculation, thermal radiation, random, featureless, carrying no information about what fell into the black hole. A black hole formed from a collapsing star made of hydrogen, and a black hole of the same mass formed from a collapsing star made of iron would, according to Hawking's calculation, emit identical Hawking radiation as they evaporated, which means that when the black hole is gone, when the last of its mass has been radiated away in that final burst, the information that fell in with all the matter that formed it, and all the matter that subsequently fell in across the black hole's lifetime, has been destroyed completely. irreversibly. It no longer exists in any form anywhere in the universe. This is the black hole information paradox, and it is not a minor technical puzzle at the fringes of theoretical physics. It is a direct, irreconcilable conflict between two of the most successful and most fundamental theories in all of science. Quantum mechanics says information cannot be destroyed. General relativity combined with quantum field theory in the form of Hawking's calculation says that black hole evaporation destroys it. Both cannot be right. One of them must be wrong, or both must be incomplete, or there is a resolution that nobody has yet found that makes them compatible in a way that current physics cannot see. Hawking himself initially took the position that information was genuinely destroyed. That black hole evaporation represented a real violation of unitarity, a fundamental modification of quantum mechanics in the presence of strong enough gravity. He called it information loss, and he defended it vigorously through decades of argument with colleagues who found it deeply unacceptable. The opposition was led primarily by Leonard Susskind, a theoretical physicist at Stanford, who argued that information loss was simply not acceptable, that it violated something too fundamental about the structure of physics to be true, that there must be a resolution in which information was preserved even in black hole evaporation, even if that resolution was not yet visible in the mathematics. The debate between Hawking and Susskind became one of the great intellectual battles in modern physics. Susskind has written a book about it, The Black Hole War, which describes decades of argument, conference presentations, private conversations, and the slow, grudging shift in the consensus of the theoretical physics community toward Susskind's position. In 2004, Hawking conceded. At a conference in Dublin, he announced that he had been wrong about information loss, that he had found a way to understand black hole evaporation in which information was preserved, encoded subtly in the correlations of the Hawking radiation, in a way that his original calculation had missed. He paid off a bet he had made with John Preskill at Caltech, handing over a baseball encyclopedia, described as the ultimate repository of information that could be retrieved at will. But Hawking's concession did not resolve the paradox. It acknowledged that information was probably preserved. It did not explain how. The mechanism by which information falling into a black hole is encoded in and eventually recovered from the Hawking radiation remains, after decades of work by some of the most brilliant theoretical physicists alive, deeply unclear. The leading candidate is a framework called holography, or more specifically, the ADS/CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997 that suggests a deep equivalence between a theory of quantum gravity in a certain type of curved spacetime and a quantum field theory living on the boundary of that spacetime. In this framework, black holes in the bulk of the spacetime are equivalent to thermal states of the boundary theory, and the unitarity of the boundary theory guarantees that information is preserved through the evaporation process. This is a profound and beautiful mathematical result. It has transformed theoretical physics in the decades since Maldacena published it. It provides a framework in which the information paradox appears to be resolved, in which information is preserved. But it does so at the cost of raising a new and equally deep question. If the physics of the bulk, the space-time inside the horizon, the singularity, everything that general relativity describes as happening inside a black hole, is equivalent to the physics of the boundary, then in what sense does the interior of a black hole exist at all? Is the singularity real? Does anything happen inside the event horizon in any meaningful physical sense? Or is the interior of a black hole a kind of computational artifact, a description that is locally valid, but that does not correspond to any independently existing region of spacetime? These questions are not settled. They are among the most active areas of research in theoretical physics today. They touch on the deepest questions about the nature of space, the nature of time, the reality of the singularity, and the meaning of quantum mechanics in the presence of gravity. The firewall paradox, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, a group now known in the field by the acronym AMPS, added another layer of difficulty. They showed that if information is preserved in Hawking radiation and quantum mechanics is valid, and general relativity is valid in the interior of black holes, then the event horizon cannot be smooth and empty as general relativity predicts. There must be a wall of high energy radiation at the horizon, a firewall that would instantly incinerate anything crossing it, which contradicts the founding principle of general relativity, which says that spacetime is locally flat at the event horizon, which says that a freely falling observer should notice nothing unusual at the moment of crossing. The firewall paradox has not been resolved. It sits at the intersection of general relativity and quantum mechanics and refuses to move. Every proposed resolution creates a new problem somewhere else in the framework. The theoretical physics community has been working on it for over a decade, and the consensus is that the resolution, when it comes, will require a fundamental new understanding of something, of spacetime, of information, of quantum mechanics itself, that we do not yet possess. This is where the physics of black holes currently stands, not at a tidy conclusion, not at a place where the equations agree and the picture is clear, at a frontier, at the edge of what the most successful theories in the history of science can tell us, a place where they contradict each other in ways that cannot be papered over or ignored, where the resolution is known to require something new, but nobody yet knows what that something is. The singularity remains undefined. The information paradox remains unresolved. The firewall hangs at the horizon of every black hole in the universe, either real or not real, and physics cannot yet tell you which. This is not a failure of science. It is science being honest about where it is and where it is, right at the edge of understanding, staring into the darkness of the event horizon, knowing that the answer is in there somewhere but lacking the theoretical tools to retrieve it, is exactly where the most important discoveries in the history of physics have always been made. The next great theory of physics will be built in part from what we learn about black holes. It has to be, because no theory that cannot account for what happens at the singularity, that cannot explain how information is preserved through evaporation, that cannot resolve the firewall without destroying the equivalence principle, no such theory can claim to be a complete description of reality. And we do not yet have that theory. We are still looking. Step back from the singularity for a moment. Step back from the information paradox and the firewall and the mathematical breakdown at the center of the event horizon. Step back from all of it and look at the larger picture. Because there is something about black holes that gets lost in the drama of the physics, in the spaghettification and the Hawking radiation and the conflict between the two greatest theories in the history of science. Something that is, in its own way, more extraordinary than any of the individual details. Black holes are not rare. They are not exotic objects at the fringes of the observable universe, detectable only by the most sensitive instruments we have ever built, visible only under the most extreme cosmic conditions. They are central features of the universe as we know it. They are woven into the structure of the cosmos at every scale, from the stellar remnants scattered through the disk of our galaxy to the supermassive giants anchoring the centers of galaxies across the observable universe. And they have been here, shaping everything, for almost as long as the universe itself. Begin with the stellar black holes. When a massive star, a star with a mass roughly 20 or more times that of our sun, reaches the end of its life, it does so in the most energetic event in the observable universe short of the Big Bang itself, a supernova. Throughout its life, a massive star has been held in equilibrium by two opposing forces: the inward pull of its own gravity, trying to collapse it toward its center, the outward pressure of the nuclear fusion reactions in its core, the energy released as hydrogen is fused into helium, helium into carbon, carbon into neon, and oxygen and silicon, and eventually iron, pushing outward against the gravitational collapse. The equilibrium holds for millions of years. The star burns, it shines, it contributes its light to the galaxy. And then the iron arrives. Iron is the endpoint of stellar nucleosynthesis. Fusing lighter elements together releases energy. That is what powers the star. But iron is different. Fusing iron together does not release energy. It absorbs it. When a massive star builds up an iron core, there is no more fuel to burn. The outward pressure that has been holding the star against its own gravity for millions of years simply stops. In less than a second, the core collapses. The outer layers of the star, no longer supported from below, fall inward. They hit the collapsed core, now a protoneutron star of extraordinary density, and bounce outward in a shockwave of unimaginable violence. The outer layers of the star are expelled into space in an explosion so bright it can outshine the entire galaxy it lives in for weeks or months. If the remaining core mass is below a certain threshold, the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 solar masses, the collapsed core stabilizes as a neutron star, an object the size of a city containing more mass than the sun, so dense that a teaspoon of its material would weigh 1 billion tons on Earth. If the remaining core mass exceeds that threshold, nothing stops the collapse. Not the electron degeneracy pressure that holds white dwarfs against collapse. Not the neutron degeneracy pressure that holds neutron stars. Nothing. The collapse continues until the mass is contained within its Schwarzschild radius and a black hole forms. In the outer arms of our galaxy alone, there may be 100 million stellar black holes, objects ranging from a few times the mass of our sun to tens of solar masses scattered through the disk of the Milky Way, the remnants of massive stars that burned brightly and ended catastrophically across the billions of years of the galaxy's history. We cannot see most of them directly. A black hole that is not actively consuming material simply sits in darkness, emitting no light, betrayed only by its gravitational influence on nearby objects. But we can infer their existence from the behavior of binary star systems, pairs of stars in which one has collapsed to a black hole and is drawing material from its companion, the infalling material heating to millions of degrees as it spirals inward and radiating powerfully in X-rays before crossing the horizon. X-ray binaries, scattered across the sky, each one a stellar black hole consuming its companion in slow motion across geological timescales. But stellar black holes, for all their violence and strangeness, are not the black holes that most profoundly shape the universe. That role belongs to their supermassive counterparts. At the center of the Milky Way, 26,000 light years from Earth, sits Sagittarius A star, 4 million solar masses. An object so massive and so compact that stars orbit it at thousands of kilometers per second. Stars that complete a full orbit in years. Stars whose trajectories have been tracked by astronomers at the Keck Observatory and the Very Large Telescope for decades, their orbits mapping out the invisible gravitational presence at the galactic center with a precision that leaves no room for doubt about what is there. A supermassive black hole. The Event Horizon Telescope, a global network of radio observatories linked together through a technique called very long baseline interferometry to create an effective telescope the diameter of the Earth, imaged Sagittarius A star directly in 2022. The result was a ring of glowing orange gas surrounding a dark central region, the shadow of the event horizon, the boundary within which light cannot escape, rendered visible for the first time. We have seen our galaxy's central black hole, and Sagittarius A star is, by the standards of supermassive black holes, not particularly large. The black hole at the center of M87, the elliptical galaxy in the Virgo cluster, whose image was captured in 2019 and became one of the most widely reproduced scientific images in history, contains 6.5 billion solar masses. Its event horizon is larger than our entire solar system. Light that crosses its horizon has been traveling for years to get there. At the center of a galaxy called TON 618, roughly 10.4 billion light years from Earth, sits a black hole containing 66 billion solar masses. An event horizon so large that light takes months to cross its diameter. An object so massive that the concept of standing near it and feeling its gravitational pull, an experience already inconceivable for stellar black holes, becomes entirely meaningless as a human scale comparison. 66 billion times the mass of our sun in one object. These supermassive black holes are not passive residents of their host galaxies. They are active participants in galactic evolution, engines that regulate the growth of galaxies across cosmic time in ways that astronomers are still working to understand. When a supermassive black hole is actively consuming large amounts of material, it becomes what is called an active galactic nucleus, or a quasar, one of the most luminous objects in the observable universe. The material falling into the black hole releases energy with an efficiency that makes nuclear fusion look modest by comparison. A fraction of the infalling mass is converted to energy, as radiation, as jets of particles accelerating to near the speed of light and streaming outward for millions of light years, as winds that blow back through the galaxy and heat or expel the gas from which new stars would otherwise form. Supermassive black holes regulate star formation across their host galaxies. They determine how quickly galaxies grow. They shape the large-scale structure of the cosmic environment in which stars and planets and life can form. The existence of life on Earth, the existence of a planet with liquid water orbiting a stable sun-like star in a quiet region of the Milky Way, is connected through a chain of cosmic causation spanning billions of years to the behavior of the supermassive black hole at our galactic center, not directly, not simply, but connected. Because the history of our galaxy, its rate of star formation, the distribution of its stars, the chemical enrichment of its interstellar medium across billions of years, has been shaped by the activity of Sagittarius A star in ways that are still being mapped out by astronomers studying the relationship between black holes and the galaxies that host them. Black holes are not separate from the story of life in the universe. They are part of it. Now step further back still, the first image of a black hole captured in 2019, the second in 2022. The detection of gravitational waves from merging black holes beginning in 2015. The decades of orbital tracking that revealed Sagittarius A star. The X-ray observations of accreting stellar black holes. The spectroscopic evidence of supermassive black holes in distant quasars. Evidence that these objects were already enormous when the universe was less than 1 billion years old. All of this, every piece of observational evidence we have accumulated about black holes, points in the same direction. These objects are real. They are common. They are central to the structure and evolution of the universe. They have been here for most of cosmic history, and they represent in the places where their physics becomes most extreme, at the singularity, at the event horizon in the moment of Hawking evaporation, the frontier where our best understanding of reality runs out. The singularity is not an embarrassing detail that a better calculation will eventually smooth over. It is a genuine signal that general relativity is incomplete, that at the densities and curvatures that exist at the center of a black hole, spacetime, as general relativity describes it, ceases to be an adequate description of what is actually there. Something else takes over, something that requires a theory of quantum gravity to describe, a theory that does not yet exist in complete form. The information paradox is not a puzzle that will be resolved by a clever trick within the existing framework. It is a signal that the existing framework is internally inconsistent in the presence of black holes. That quantum mechanics and general relativity, applied together in the context of black hole evaporation, produce a contradiction that can only be resolved by fundamentally revising one or both of them. This is where physics currently stands, not in confident possession of a complete picture, not with a theory that describes all of reality from the Planck scale to the cosmological horizon in a single, consistent framework. Standing at the edge of what it knows, looking into the darkness of the event horizon, aware that the resolution of the contradictions it has found will require a conceptual leap of the kind that has only happened a handful of times in the history of human thought. The leap from Newtonian gravity to general relativity. The leap from classical mechanics to quantum mechanics. The next leap, the one that resolves the information paradox, that replaces the singularity with something physically meaningful, that unifies quantum mechanics and gravity into a single, coherent framework, is still ahead of us, and black holes will be at the center of it, not as objects that need to be explained away, as the key, as the place where the contradictions are sharpest, and therefore where the new understanding will be forced into clarity first, as the cosmic laboratories where the extremes of physics become unavoidable and the inadequacy of current theories becomes impossible to ignore. Every time we have looked more carefully at black holes, we have found something we did not expect. The smoothness of the event horizon, the Hawking radiation, the holographic principle, the firewall. Each unexpected discovery has pushed the frontier of understanding further, and forced a deeper engagement with the most fundamental questions about the nature of spacetime and information and reality itself. The James Webb Space Telescope is finding supermassive black holes in the earliest galaxies, objects of extraordinary mass that existed when the universe was only a few 100 million years old, far earlier than our current models of black hole formation predicted. We do not yet know how they got so large so fast. The answer, when we find it, will change our understanding of how the universe evolved from the hot, dense plasma of the Big Bang to the structured cosmic web we observe today. The next generation of gravitational wave detectors, LISA in space, the Einstein telescope and cosmic explorer on the ground, will detect merging black holes across the entire observable universe. They will map the population of black holes in a way that current instruments cannot approach. They will probe the dynamics of spacetime at its most extreme with a precision that will test general relativity in the strong field regime where its predictions have never been directly verified. The answers are coming, slowly, through the accumulation of observations and the development of theory, and the kind of sustained intellectual effort that does not announce itself with a single dramatic moment, but proceeds steadily, patiently, across decades and careers and generations of scientists who pass the questions on to the next generation when they have taken them as far as they can. The answers are coming, and when they arrive, when we finally understand what happens at the singularity, when the information paradox is genuinely resolved, when quantum mechanics and general relativity are unified into a theory that describes all of reality from the smallest to the largest scale without contradiction. When that happens, we will look back at black holes not as the places where physics broke down, but as the places where physics grew up. The places where the universe forced us to think more carefully, more deeply, more honestly about what space is, and what time is, and what information is, and what it means for something to exist. The places where the comfortable assumptions dissolved and the real questions became impossible to avoid. You live in a universe full of them, at the center of your galaxy, at the center of every large galaxy in the observable universe, in the stellar remnants scattered through the disk of the Milky Way. In the early universe, forming faster than our models predicted, growing to sizes that our theories struggle to explain, black holes are everywhere, and they are still, after a century of general relativity and 50 years of Hawking radiation and decades of gravitational wave astronomy and direct imaging, not fully understood. Which means the investigation continues. Which means the most interesting discoveries about these objects are still ahead of us. Which means that the darkness at the center of the event horizon, the region from which no light escapes, from which no information returns, from which no signal of any kind can reach the outside universe, is not the end of the story. It is the beginning of the next chapter. If this changed the way you see black holes, the places where physics completely breaks down and where the deepest questions about the nature of reality remain unanswered, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.